we present Chupa, carving 3D clothed humans from skin-shaped priors using 2D diffusion probabilistic models. Our method is capable of generating detailed, clothed human avatars from an initial simple X pose parameter set, while further controlling the human identity using optional text prompts. While the creation of human 3D models has been of high interest in many fields, most previous approaches tended to be limited in generating realistic models with diverse identities and clothing. Our method aims to solve 3D human generation by dividing the problem into 2D normal map generation and 3D reconstruction. In detail, given an simple X parameter and an optional text description, our diffusion model generates detailed normal maps of the frontal and backward regions. Afterward, the normal maps are used to carve the simple X mesh into a clothed, realistic human mesh. This pipeline allows us to leverage the image generation capability of diffusion models towards 3D generation. Now let's dive into the details. To efficiently generate pose-conditioned normal maps, we combine the latent spaces of autoencoders and conditional diffusion models. Specifically, we first use 3D human datasets to render detailed human normal maps and their corresponding posed simple X normal maps. We then train a vector-quantized autoencoder to encode normal maps into a perceptually equivalent latent space, which is then used to train the conditional diffusion model. During inference, the diffusion model samples the latent codes corresponding to detailed normal maps, conditioned on the simple X normal map. Note that we generate both frontal and backward views of the human body at once, in order to generate holistic geometric details in a visually consistent manner. With separate generation, we may get inconsistent geometry due to the randomness of diffusion models. On the contrary, our dual generation scheme produces consistent geometry of a single identity and clothing. Once both detailed normal maps are prepared, we create a detailed human mesh by carving the initial posed simple X mesh according to the normal maps. To do so, we optimize the 3D vertex positions of the initial simple X mesh using a differentiable rasterizer. This involves minimizing the loss for the normal maps and masks, between the ones rendered from the rasterizer and those generated from our diffusion model. To improve the side view, we introduce a side loss to encourage the mesh to have a larger mask than the simple X mesh. For geometric regularization, we exploit Laplacian loss and normal loss to get smooth geometry of the mesh. Please refer to our paper for the details. We optimize the mesh in a coarse-to-fine manner, where the number of vertices is gradually increased, capturing the finer geometric details throughout the process. Here we show the overall process of our normal map-based optimization. With an initial simple X mesh as a strong geometric prior, we were able to generate meshes with appealing 3D geometry. Up to this point, we already have a 3D human mesh with fine geometric details. We can choose to further refine the mesh quality through a diffusion-based resampling technique. We first render the normal maps of the previously optimized mesh in multiple views. Then, using the same diffusion model, we resample the rendered dual normal maps to improve the visual quality without altering major details. To enhance the facial details of the mesh, we also train a separate diffusion model on the normal maps in close-up view, and exploit this model to resample the rendered faces. The refined normal maps from multiple views are subsequently used as inputs for the 3D mesh optimization stage, generating a 3D human mesh with better details. The mesh before and after the refinement. You can see the better face quality and smoother overall geometry after the refinement. We can also choose to use optional text descriptions of the human identity and clothing. By fine-tuning a pre-existing text-to-image diffusion model, we first create a frontal normal map from simple X and text conditions. Then using our original diffusion model, we perform a channel-wise inpainting to create the backside normal map based on the text-consistent frontal normal map. Here is the comparison between Chupa and the previous state-of-the-art. When randomly generated from the same simple X parameter, our results show better geometric details with distinctive identity and clothing. By controlling the shape and pose parameter of the simple X model, we can generate 3D human meshes with various body shapes and poses. You can see the results align with the given body shapes and poses while presenting various identities and clothing. We can also further control the identity and clothing with a text prompt, making our scenario intuitive for digital avatar creation. Thank you for listening.